Okay, so this is lecture 77. We're going to talk about general relativity. Obviously, we're not going to go into a great deal of detail. General relativity is mathematically intensive. It requires a type of math beyond even calculus called tensor mathematics. Tensors are not as tough as people make them out to be. They're really just kind of glorified vectors. But that's a tangential detail. But let me also state that I'm not an expert in general relativity. I'm not a cosmologist. Those tend to be the kind of people that really specialize in this stuff. But I do know a thing or two about it. But just want to point out that I may say something stupid, and that happens. But as physicists, we don't know everything, even though sometimes we claim to. But it's usually in jest. For example, Sidney Coleman at Harvard walked into a room one time while Steven Weinberg was giving a lecture, and Weinberg had said, "I don't know the answer to that question." And Sidney Coleman, having just arrived in the room, said, "Well, I do. What's the question?" He's joking, but anyhow, physicists are just as confused about things as every other person, I think. Somebody asked Linus Pauling one time how he had so many good ideas. He won 2 Nobel Prizes. And he said, well, because I had a lot of bad ideas. So in order to have a few good ideas, you got to have a lot of bad ideas. So hopefully this is not one of those bad ideas. Try to lay out the general idea here, okay? But first I want to recall from the last lecture we talked about fictitious forces, right? Yeah. And for example, we had, I guess we'll call it the braking force. This is that force that you experience when you're in the car and somebody slams on the brakes and everything goes flying forward, right? As if there was some fictitious force attracting everything towards the windshield, right? And we found that this force, we'll call it F sub BR, was equal to the mass times whatever the acceleration was from the brakes, right? We also had the centrifugal force, call it FCG maybe, and this is basically it's kind of the inverse of the centripetal force, right? Centripetal force is what you would note if you were in an inertial reference frame making an observation about it. It's v squared over r. And finally, we talked about the Coriolis force briefly, and we'll call that CR, and that was equal to the mass times omega times the velocity, which is kind of interesting, right? It's a force which actually depends upon the velocity. But notice that in all 3 of these forces, right, there's a mass term in there, okay? Okay, so we can call these inertial forces, if we'd like. It's a good name for them. Inertial forces, because they all contain this term with the inertial mass in it. Now recall that Newton's law of gravitation, call it G, well that sounds like it's general relativity, doesn't it? I call it F sub Newton. How's that? No, universal, UG. One more time. F sub UG, right? This was an actual force law, Newton's law of universal gravitation, which said that the force was big G, big M, little m over r squared, right? Now, should I write this m a little different? Well, let's just note that this mass term here is called the gravitational mass. The big M is the gravitating body. This could be the sun, for example, and little m would be the earth. But in this term, because this is a real force, right, we would call this the gravitational mass, because it's the force involved in this gravitational attraction, right? Whereas these forces are all these inertial forces, right? These are really just a result of things wanting to continue on in a straight line and don't want to be interrupted from that, right? And so these are things that result when they resist. They have something that causes them not to travel in a straight line, right? So to a very high degree of accuracy, I think 1 part in 10 to the 11, which is a really big number, the gravitational mass and the inertial mass have been found to be identical, okay? And Einstein thought, well, this is probably not a coincidence, okay? That these forces are identical, or excuse me, that these masses are identical. And this is kind of the starting point for his ideas in general relativity and what he called the equivalence principle. At least I think he called it the equivalence principle. Maybe people afterwards called it that, I'm not sure. So let me describe what that means. But first, I've got a couple of scenarios up here. On this side, we have a couple of rocket ships out in deep space. Okay, one of them, they're traveling at a relative velocity between them, right? So we call this one the stationary one. This one is moving with some speed called v naught. Okay? So there's a relative velocity between them, but there's no acceleration involved. Okay? The thrusters are off. Over here, I've drawn a couple of rockets. One, stationary on a infinitely flat planet, such that it provides a completely uniform gravitational field everywhere. Okay? Or approximately like Earth. Okay? But really we need it to be infinite in extent, and I'll explain why that's the case later in the lecture. On the right, we have a rocket ship somewhere out in deep space, far from any gravitational fields, just like these guys over here, except this one is accelerating with an acceleration that exactly matches the acceleration of gravity here on Earth. Okay? So on the left-hand side, if we were to track any point, say on the moving rocket, we could write down the kinematic equations for this. This is going to just be y prime equals y minus v naught t. And if I were to graph y, t, y, a space-time diagram of some point, for example, y equals 0 here, but y equals 0 in for the primed frame, looks like this in the unprimed frame. It's supposed to be a straight line. I think it kind of looks like it. Y equals 1, for example, which is a straight line here, would also be the line with the slope here, The slope is proportional to its velocity, Y equals 2, we could write another one, and at 2. Okay? So here, on the left-hand side, we can transform back and forth between the prime and unprimed frames, but we're taking straight lines into straight lines. Okay? So that's the situation that we get in Galilean relativity, and even in special relativity, where things are always moving at a constant velocity. They may just be moving very quickly, and so it gets a little more complicated. Like t prime is not equal to t in special relativity, And so we have to use the Lorentz transformations, but they're still linear. Okay? Over here, what's going on? Well, here, if we write the same transformation equation, we write y prime is equal to y minus 1/2 gt squared, This is, if you go back to the kinematic days, this is just because we have a uniform acceleration, If we start with the acceleration as a constant, we can work our way up to the velocity as the acceleration times the time, to the area under that curve, it's the triangle, you remember the triangle, 1/2 g times t squared, okay? So what does that space-time diagram look like? There's y equals 2 again, but this time, instead of straight lines, for the accelerating rocket, we get parabolas, There's that, it looks like it's rounding down, but it should really just always be growing out. So this is y prime equals 0, this is y prime equals 1, this is y prime equals 2. Over here I should have labeled them as well. Y prime equals 0, y prime equals 1, y prime equals 2. Okay? So Einstein noticed or suspected that there was a connection between these curvilinear coordinates and gravity. Okay? And so you have to ask yourself, could you really, if you were in one of these space capsules, and it was completely isolated, or insulated rather, so no sound from outside could get in, you wouldn't feel any vibrations from outside, okay? All you could do is detect acceleration, so maybe you have an accelerometer in your hand, okay? Could you tell the difference between being on this uniform gravity planet, Earth, or accelerating with the acceleration g in your rocket ship in deep space? Would you be able to tell? No windows, nothing,
Accelerating with g in the rocket ship?
Yep. So that if I, for example, if I'm in my rocket ship and I'm not accelerating and I have a pen and I let go of it, it's just going to sit there, Because I didn't give it any accelerations and there are no forces, Yeah. But if I'm in this accelerating rocket ship and the rocket is accelerating upwards with g, And I let go of this pen, it's going to drop just like that, okay?
Okay.
Why? Because of what we call the braking fictitious force, Yeah. Remember that? So Einstein is saying that maybe these two systems are equivalent. Now, most people back in the day would have said, well, that just seems trivial. Of course, we suspected that the gravitational mass and the inertial mass were the same masses. They probably didn't even name them. I don't know if they did or not, but they may not have even named them or distinguished between them. I'm not exactly sure who the first person to distinguish between them was, but Einstein did ask the question first, I think. Was the inertial mass the same as the gravitational mass, and what are the consequences of that? And I think a lot of people would have wished that they might have noticed this first, because the consequences were pretty profound, and I'll get to those in just a moment. But let me just point out that this is true, right, for uniform gravitational fields. There's a total equivalence between this accelerated reference frame and this reference frame that's stationary in a gravitational field. Okay?
Okay.
So what do I mean by uniform? Well, let me just change an aspect of it here for you. The Earth does not provide a uniform gravitational field, does it? Right? If this is the Earth, and here's the equator, try to make it look like a sphere, right? We can imagine, well actually let's keep it in 2 dimensions. I think that's the best. We'll do a 2-dimensional representation of the Earth. I can imagine that if this is the center, right, and I go out to some point, I'm going to draw in a different color, I think. Say a point here, which is a distance r. Okay? But there's also, if I make a perfect circle around this, I can find another point r over here, right? See that? I could find another point, say over here. It's also a distance r. Remember, the force is proportional to 1 over r squared. Okay? So if we keep the mass of the Earth fixed, and we keep the object that we're talking about, you know, the inertial test mass, we'll call it, right? And we put it at these 3 different points, the gravitational force will be the same, right? Because r is the same. It's the same distance away from the center of Earth, right?
Yeah.
Yeah? Make sense?
Yeah.
But imagine that I had a spaceship that was really big. You can see it's pretty big compared to Earth, right? So here's the Earth. Here's my little laboratory, right? Which is not very little. It's quite big, right? It's almost as big as the Earth, you see?
Yeah.
And so if I consider some point here, right? Notice that R2, right, is not the same as R1. If it's perfectly symmetrical, R1 and R3 may be the same distance, right? But R2 is not, right? R2 would appear to be a smaller distance, right? So if I were to draw kind of this equipotential surface, right, around here, not so great looking. Yeah, something like that. So at the distance R1, which I'll label this R1 also, just so we are clear about that, right? At that point, the gravitational force is the same. But here in the center of my craft, I experience a smaller gravitational force. Do you see that? So it's not uniform anymore, okay? It's not the same everywhere. It's certainly not the same along this dimension, right? Because here, this point and this point are clearly at different separations, distances from the center of the Earth, right? So the force of gravity will be stronger here and weaker here, okay?
Okay.
If we look at these 2 points, right, what are they doing? Well, there's if we think of this as like a force vector, right? These points, the ones I drew as circles, are tending to kind of squish everything inward, right? This one is pulling stuff that way, this one is pulling stuff that way, okay? They're pulling equally in this direction, right? But here they're in opposite directions, yes? You see that? And then the x points, right, how do I best draw this? Let's just do it like this. The x points, right, have a kind of a stretching, right? If the gravity at my head, if my head is up here, right, is weaker than the gravity at my feet, that means my feet are being accelerated quicker than my head is, right? Which means I'm kind of being stretched, right? Because of these 2 points here, the ones I drew here, right? This is kind of a squishing, right? We call this spaghettification. It's a hard word to say. It's like you're being stretched, and we say spaghetti because if we stretch a spaghetti noodle, it'll get longer, but it'll also get thinner, right?
Yeah.
And so we have this kind of squashing action in this direction and this stretching action in the other, right? And so these are come under the general heading of tidal forces, okay? So in anything other than a truly uniform gravitational field, the equivalence principle is not right, okay? There is a difference, right?
Yeah.
The accelerating rocket would not have these kind of tidal forces, okay? So there's no equivalence there. But if we make the assumption of a uniform gravitational field, then there is an equivalence, okay? And so now let's look at one of the consequences of that. So there were a few predictions that general relativity made, okay? And the first one that really confirmed it was this issue regarding the precession of the perihelion of Mercury, right? Remember that's the farthest away point, perihelion. So if I draw, say, the sun here, And then let's say that Mercury, which is a fairly elliptical orbit, but it's not as extreme as what I'm going to draw here, okay? Apogee is this point of closest approach, right? And then the perihelion is the farthest away point, okay, here. And it had long been observed, right, that there's this precession in the perihelion of Mercury. So that over time, what ends up happening, if I can draw this well, I should draw my sun a little smaller. I'm not going to do a very good job with this, but I'll try. I should put the sun closer. That's what the big problem is here. Sun. There's this precession in the perihelion. That's, of course, it's nowhere near that big. In fact, I think the actual number is something like 0.01 degrees per 100 years. So every 100 years, it moves by 0.01 degrees. Okay, so it's very small, but it had been observed for a long time, and Newton's gravitational theory did not predict this, right? It didn't account for that. And general relativity does, as it turns out. Okay? So if we use the Einstein field equations, we can get that. So that was the first like confirmation. The second one, which I think was actually an experiment that was done first, but the results weren't ready for a few years, so it took some time for the data to be published. It has to do with the bending of light. So Einstein observed, using this equivalence principle, that light in a gravitational field should bend. And so let's look at what that means from the try to understand it from the perspective of the rocket. Okay. So if these two are equivalent, we can analyze this from the perspective of a rocket. And what would a rocket look like? Okay, so if a light beam were to enter into the rocket at t equals 0 through a little hole, right, the rocket is accelerating upward, right? There's an acceleration. All right? And so if the acceleration is quick enough, then you see that the light, which travels in a straight path, so we're looking at it from the inertial frame, the light just travels in a straight line. The rocket ship, I guess I could put thrusters on it if you wanted, right? Is accelerating upwards, and so we see it makes perfect sense, right? Yeah. That's what it would do, right? So as it's moving across, maybe it's here when it enters, it's here at this point, and then the light is here. It's, these are photons, so maybe it's a light pulse if you want, right? But what does it look like inside the rocket frame itself? So if we were in the rocket, right? So now I'll make my observer in the rocket. Here's the hole it enters. What does it do? Assuming that our acceleration, right, is, 1/2 gt squared, right? It follows a parabolic path. You see?
Yeah.
That's what it looks like from our point of view. And so we're like, well, there's this inertial force which is bending the light, right? It's causing its path to change. It was actually confirmed. So if I make this the sun, say over here is the Earth, right? The idea was that they did during a solar eclipse. Why a solar eclipse? Because then the sun is kind of blocked, and so you can use your telescope to look around here. And so what they saw, right, was there was this star whose position they knew what it should be. I'll draw it here. So if we backtrack this up, it makes the apparent position of the star. That's a terrible looking star, isn't it? There. All right, so the star is really over here, right? But it looks like it's over here. It's because the light from the star bent around the sun, okay? And appeared to be there, all right? Does that make sense?
Yeah.
And so you could observe this during the eclipse, okay? That the position of the star, it just jumped from where it should be, okay?
Okay.
So that was a kind of the experimental confirmation of that. Another prediction made by general relativity is something called gravitational redshift, and we will talk about that when we talk about waves, okay? So I'm not going to get into it now. There's no reason to describe it to you because we haven't talked about regular, like waves and light is a wave and Doppler shift and stuff like that. But when we get to that stuff, we will talk about this. It's not that difficult. And then a last kind of prediction, I guess you could call it a prediction of general relativity, is black holes. Another prediction, I guess there are 5 now, of general relativity is this idea of a gravitational wave. Okay? So a problem that plagued Newtonian's universal gravitation law is this action at a distance problem. It really bothered them that, well, what is it that's pulling, right? I mean, if the Earth is pulling on this pen when I release it, right? Where's the hand that's pulling it, right? There's no there's no mechanical mechanism that's in that model, and this bothered people. We can kind of get around that. I think we'll do a lecture soon. I may do one on gravitational fields, and the whole field idea, but I'll probably save it until we get to do some electricity and magnetism, because it's pretty much the same model when we talk about the electric field versus the gravitational field. So I'll probably put it all in there. And so we'll kind of revisit gravity when we do that. But this idea that things can happen instantaneously. So imagine that the Earth is in its orbit, right? Light takes, I think, 8 minutes to travel from the sun to the Earth. So if the sun just disappeared all of a sudden, right, would the Earth just instantly start traveling in whatever straight line it happened, whatever direction it happened to be going at the time the sun disappeared? And the answer is no. It would take 8 minutes before the effect of the sun being gone would be noticed by the Earth. Okay? And you can kind of think of this as the propagation of a gravitational wave, which is a thing that carries energy, right, like other waves do, but travels at the speed of light. Okay? And so it would be 8 minutes. So we'd continue to orbit a sun that's no longer there, and then after 8 minutes, we would then start traveling in whatever direction we happen to be going at the time. Okay?
Okay.
So it kind of explains in a way this action at a distance issue, right? This field theory, this idea that energy can propagate through the gravitational field. I realize it's probably vague and abstract and doesn't make a lot of sense to you at the time, but right now. But maybe when we start talking about the field concept, it will make a little more sense. Okay?
All right.
So any questions about general relativity? And I mean, I'd write down like the Einstein field equations for you, but they wouldn't make any sense at all. It wouldn't be illustrative in any degree. I mean, like with special relativity, I think I showed you how in the limit of slow velocities, it reduces to just Galilean relativity, and that's useful, right? But I cannot easily show you that with general relativity, how it reduces down to Newton's laws, but it does. You just have to take my word for that.
All right.
Any questions?
No.
Okay, that's it.